All right, just trying to check if I don't know what this is about here, guys. Add this number to ICT group or send the link. Okay, well, I don't know if I'm part of guys here, but hey, just wanted to find out if you can hear me. Right, this is Shwesa Gloria, guys. Add this number to ICT group. Wow. Okay. Can you hear me?
Yes, sir.
Okay. Sorry, I'm 2 minutes late. Yes, I'm coming from another class, a number of makeup classes here, right? Very sad, but life is sad, I guess. So we are going to continue our discussion from where we left off, but I just wanted to find out if people have questions. I think we parted ways when we were discussing different techniques or approaches that you can use, right? Even the study group. Oh, I didn't know there was a study group. This is good. But why would you have two groups, ICT group and study group? Why? So we got to a stage where we were just comparing two different techniques for converting large binary numbers to decimal, right? So we're saying we could take advantage of what we term as repeated multiplication, right? That's probably the easiest because it turns out that that technique can be applied to so many different scenarios. But also we realize that we can actually convert a large binary number by first of all converting it to hexadecimal, right? So split it up into nibbles, right? Groups of 4s, and then convert the groups of 4s into decimal, and then those things, because when you're going from hexadecimal to decimal, you convert the hexadecimal into decimal. So you convert the decimal equivalents into, so you convert the hexadecimal into decimal, right? So what we were saying is that if we have something of this sort here, there's a large number here. I don't know. Oh, so this large number here, instead of using repeated multiplication where we multiply each one of these different. Your screen, sir. Oh, okay. Thanks a lot. I didn't share my screen yet. Sorry about that. Thank you for that, sir. So if we have a situation where we we are wanting to convert this number here, 1011 00110, right, into decimal, where we're saying this is the ones place, this is the twos, this is the twos place. Fours place, I'm actually even split up the number into groups of 4s like so, right? Once we split them into groups of 4s, we're implicitly converting to hexadecimal, and then we go through a process of converting a hexadecimal number into decimal. It's much easier because what you'll be working with now is powers of 16. 16 to power 0, 16 to power 1, 16 to power 2, 16 to power 2, right? That's it. It makes life a lot easier. But as earlier mentioned, whatever works for you, I suppose. So if there are no questions, then we will continue now, where we start looking at basic arithmetic associated with binary numbers, right? And we shall start with binary addition, right? So here's the thing. It turns out that when you're adding, let's say you want to add two numbers, 0111 and 0110. The easiest thing to do here is you just convert, you're saying the easiest thing is you just convert the numbers into decimal, and then you add them and convert the answer into binary. That would be like cheating, right? Because there's a reason why we're doing this. So what we're saying is that an approach to take, if you're asked to add 0111 and 0110, what we're saying is, or rather add 111 and 110. What we're saying is you could just convert 111 into decimal, right? This is the ones place, this is the twos place, This is a false place. So it's 4 plus 2 plus 1, which is 7. So effectively, we're saying we are adding, you convert that to the thing, you're adding 7 and this is the ones place to 7 and 6, right? Which is 13, is it? So we get 13 and then we would say we convert the 13 into binary. And converting 13 into binary is pretty easy here. All you would do is just repeatedly divide your 13 by 2, right? And then you'd say the answer is just going to be 2 into 13 is 6 times remainder 1, right? 2 into 6, the answer is 3, remainder 0. Now this is retarded though. It's not. We're trying to understand how the computer does this, right? Which is why we need to do it the normal way. But what we're saying is this is the logical thing to do. You convert the numbers you're adding into decimal, add the decimal numbers, and then convert the answer into binary. Because this is what you're used to, right? So 2 into 3 is 1, remainder 1. And then 2 into 1 is 0, remainder 1, right? So in fact, the answer is 1101, right? So 1101. So this is what we're saying. This is what would obviously come natural to us, yeah? But we want to be able to add numbers just like we add in base 10 here, right? So it turns out that a very simple way of adding numbers, binary numbers, is just by following simple rules. More rules now. Welcome to rules, more rules, right? And the rules are simple, right? The rules associated with the result that you expect to get as you are adding the different combinations of bits, right? So what we're saying is when we add a 0 bit and a 0 bit, we get 0. When we add a 1 and a 0, we get 1. Now I know what you're thinking, but Lighton, what about when you add a 0 and a 1? Oh, a 0 and a 1 is the same as a 1 and a 0. But if you want, we can put it here. Say rule number 5. When you add a 0 and a 1, the answer is you drop down 1. It's one and the same. Drop down 1. We'll call this rule number 5. All right. When you are combining a 1 and a 1, you carry 1 and then you drop 0. Right. So the answer is 0. The remainder is 1. When you are, and this is an important rule, by the way, when you have a situation where you are adding 1 and 1 and 1, your answer is 1, or you drop 1, and then you will carry 1 as the remainder. You move it forward. Now, this idea of carry 1 and whatnot is the same as what you do when you're adding decimal numbers. You remember what Miss Banda told you when you're saying in grade 1, I guess, I don't know if it was primary school or something, but when you are adding 9 and 2, what is 9 and 2? 9 and 2 is, now this is probably a bad example here. Let's do 109. What is 109 plus 1? What is the answer here? What is the answer? I know you know the answer here. What is the answer when you add 109 plus 1? I don't know, right? But anyway.
110.
Exactly. So this idea of 110. Yeah, but think about this for a second. 110, it's not like it's going to be 110. What Miss Banda told you is you add 9 and 1. What is 9 and 1? It's 10. So you say it's 0, remainder 1. The 1 goes to the next placeholder, right? And in fact, you're going to add 1 and 0. It goes to the 10th place. This is the 1's place, 10th place, 100th place, 1000th place, right? And 10th place or something. So what we're saying here is it will be 1 plus 0, it's 1. And then you have 110. This is how you get 110. We are saying the same thing applies to base 2. When you are adding, when you are faced with a situation where you are adding, this is why we say drop. When you're adding 1 and 1, we are saying that because there is no 2 here, we are saying here the answer is going to be 0. And then we carry the bit to the next placeholder. Do you understand? This is what we're saying by saying 1 and 1, we carry 1, we drop 0. 1, 1, 1, we have, if we're adding 1, 1, and 1. What we're going to have is a situation where the answer is we drop 1 as the answer, as part of the answer, we will drop 1 and then carry the other one to the next placeholder here. Now again, I know what you're thinking, well, Lighton, why would we have 3 1s, right? In case you're wondering, like Lighton, I guess probably wondered at some point when you was learning binary for the first time, imagine a situation where you're adding 1, 1, and 1, 1, right? When you're adding 1, 1, and 1, 1, what is 1, 1? 1, 1, 1 is 3, right? When you're adding 3 and 3 in binary, what you're saying is the first part here, 1 and 1, it's 0. Remainder, 1, when you carry 1, the 1 is going to be carried on top here. Because it's carried on top to the next position, you will have 3 1s. So we need a separate rule for these 3 1s here, which is why we have that last rule here. Do you understand?
Yes, sir.
Yes, sir.
This is why we have this thing here. All right. So
yes.
now that we set the stage for these rules, these 4 basic rules, we are now going to just see if we can play around with these. We're going to go through the rules again, but we want to see some basic examples of how to apply these rules, right? And then, oh wow, I don't know. And then we can do this. So again, just to kind of show us what's happening here, we're saying these are the rules here, right? So first rule is where you have zeros, right? You just drop down a 0, right? The second situation is where, and again, you notice that this visualization has a situation where perhaps you might have 3 digits that you're working with, right? It's possible you might be just adding 2 digits, but there are instances where you have 3 digits, right? So this is what we are showcasing here. We're saying if you have a situation where you have 3 digits like so, 0, 0, 0, it's 0 is the answer. You carry 0. If you have a situation where you have a 1 and 2 zeros, the answer is just 1. You carry 0, right? And of course, where you have this 1 is inconsequential. I mean, it could have been here, it could have been at the end. But what we're saying is just a situation where you have 2 zeros and 1, 1. The answer is 1. You carry 0. When you have 2 1s, the answer is 0. You carry 1. When you have 3 1s, the answer is 1. You shall carry 1. And again, I just wanted to mention that this idea of carrying is you move it to the next 2's place, right? So you have the 1's place, you have the 2's place, you have the 4's place, you have the 8's place, you have the 16's place. So as you are adding numbers, if there's a carry bit, you move it to the next placeholder, right? So let's just play around with just a few examples and try and see if we can reinforce this. Hopefully this is probably going to make sense. I think it will. So let's say we are adding 1 0 1 1 and 1 1 0 1, right? Effectively, what we're adding here is 1 plus 2 plus 8, right? Which is 11 here. This is 11, is it? 1's place, 2's place, 4's place, 8's place, right? 8 plus 2 is 10 plus 1 is 11. And then we're adding 11 to 1 plus 4 plus 8, which is 13. So we're adding 13 and 11 here. The answer should be 24, right? Yes? Isn't this 11? Am I on my own here? What? Fine, we'll use a calculator. I know. Yeah, well, we don't know. I'll use a calculator. 1011 10. Can I finish? It's 1011 converted to decimal is 11. 1101 converted to decimal is 13. So effectively, what we're saying here. Here's the thing. There's a reason why I'm converting these to decimals first. When you're doing this for the first time, for you to be able to follow through with what you're doing, just convert them to decimal first, because for you, decimal is more intuitive. You've been doing this since grade 1, in fact, since kindergarten or something. So convert these numbers to decimal first, get the answer, and then try and see if you can work backwards, right? So what we're saying is we are wanting to have a situation where we get 24 as the answer. Whatever answer we're going to get here should be 24. This is what we are saying here. Should be equivalent of 24. Yes, there was a question? I thought there was a question.
I was lost on how you, yes, sir. I was lost in how you were doing the additions. Since you started converting them back into binary as 11 and 13, that's when you add them. You convert them into binary, that's when you add them. And how
No, I'm
exactly are you doing
saying,
that?
no, I'm not saying that's not what we're going to do, but I'm just saying that the simplest thing to do for you right now, before you master these things here, these rules we're talking about, yeah? The easiest thing for you to do when you're adding two binary numbers is you do what? You convert them to decimal, you add them up, and then you get the answer and convert the answer to binary. And in fact, I'm further saying that as you are practicing to reinforce these rules, to get to understand how you go about adding binary numbers, it will be in your best interest if you first of all convert the binary numbers that you are adding to decimal, add them up, and then get the answer in binary before you understand the rules. But eventually you understand the rules, which is what we're doing next, right? So we are adding 1011, which is 11, and 1101, which is 13. To follow the rules, if you remember the rules, when you are adding 1 and 1, what do we get? 1 and 1, we carry 1, we drop down 0. In fact, the answer is 0, carry 1. So in here, the answer is going to be 0, we carry 1. Now, what I'm doing here for you to follow through, for those of you that, and I know some of you already know this, but for the benefit of those that are not very familiar with this, what I am carrying over is going to be in this column, in this row, sorry. The answer is going to be in the last row. Do you understand? So pay particular attention to the change in values in this row and this row, right? Again, I'm just going to start working backwards here so that we understand we're on the same page. When we're faced with a situation where we have 1 and 1, the answer is 0. We carry 1, meaning that we move it to the next 2's place, which is the next one here, right? And maybe I should have also included 0, it's fine, 1's place, 2's place, and whatnot. All right. So you notice now that this next column, which we need to add, has a 1, 0, and a 1, which we carried from here. So effectively, we have a 1, 0, 1. If we go back here, when we have a situation where we have a 1, 0, 1, 1, 0, 1, the answer is 0. We carry 1. So I'm going to go back here. We're in here, 1, 0, 1. What is the answer? It's 0. We carry 1. We have a similar situation here where we have a 0, 1, 1. What do we do when we have a 0, 1, 1? We come here, we see here, 0, 1, 1, right? Sorry, 0, 0, 1, 1. The answer is 0, we carry 1. We're going to go back here, 0, 1, 1, 0, the answer is 1. Boom. The last part is where we have 1, 1, 1. What is 1, 1, 1? It's the last case, right? Where we are saying, when we have 1, 1, 1, we drop 1, we carry 1. Now it's called an overflow, right? If you were working with, not if, but we're working with 4-bit representation, but you notice that our answer has 5 bits. Why does it have 5 bits? Because the resulting number is significantly larger, right? So in fact, the answer is 1, 1. The carry bit here, this is effectively 0, 0, 1. So it's 0, 0, and 1. We just drop 1, right? So the answer is 1, 1, 0, 0, 0. And in fact, if you convert this, you notice that it's 24, right? 2 to the power 0, 2 to the power 1, 2 to the power 3, 2 to the power 4, 2 to the power, 2 to the power 0, 1, 2, 3, 4, right? 0, 1, 2, 3, 8, 4, 16. 16 plus 8 is, I don't know, 24, right?
Yes, sir.
Yeah. So here's the thing, right? I hope it's going to make sense here. It's a rules, and the rules really, they are simple rules. If you think about this, it's just 3 rules really. 0, 0 is 0. 0, 1 is 1. 1, 1, 4 rules. 1, 1 is 0, remainder 1. 1, 1, 1, 1 is 1, remainder 1. It can be a bit confusing at the beginning when you have an overflow like here, right? You must just remember that whenever you carry something forward to the next placeholder, just carry it forward and assume that the things on top here are just zeros. Yes? Good stuff. So here's another way of looking at this. Let's say we have this number here, right? A relatively large number. Effectively, what we have here is, what number is this? This is 1 plus 2. This is 0, 1, 2, 3, 4, 5, 6. It's 2 power 32. So it's 64 plus 32. Anyway, let's not do this. I just don't want to go around in circles here. So we are saying 1, we can actually convert it to, you can convert this to, instead of using a calculator, if you want, you can, in fact, let's do this. Let's not get into the habit of using a calculator, right? Let's say you're still getting used to the rules and you want to just convert this to decimal. Easiest thing to do is nibble, right? Split it up, half a byte, like so. So we know that this is, in fact, this is what? 0, this is 1, 1. This is 1 plus 2, which is 3, plus 8, which is 11, right? Yes? 0, 1, 2, 3, 8. 8 plus 2 plus 1, 11.
Plus 6.
And then this is, thank you very much. This is 6. Then we do the same thing for this particular number. We split it up into nibble, and you notice that the magnitude are slightly different for these numbers, right? This is much large. This is a much larger number than this one. We split it up into half. In fact, we can finish this off and just convert it to decimal, right? This is 16 to power 0, right? Which is 1. This is 16 to power 1, which is 16, right? Yeah. What is the answer here? We're still using a calculator, I guess. It's 16 times 6, which is 96 plus 11, right? Are we doing this? Is this, I don't know if I have the correct 107. I don't know if it's a correct answer. But also what you can do, right? What you could have done here is just, well, like, why are you doing that? You can use a calculator 1101011, and then convert this to decimal 107, right? So we can do the same here. And the reason I'm working this backwards is I'm trying to latch on to what we've already discussed, right? Some of the things we've already discussed so that they sink in. This is why I'm doing this, by the way. So we're saying for this particular large number here, we do the same thing. We convert this to, because repeated multiplication is difficult for a large binary number like this, what we want to do is splice it up into nibbles, right? Or half a byte, 4-bit representation. So we have 1110. What is the answer here? 1 plus 2 plus 4. Isn't it 7?
7.
Okay. What is 2 plus 8? What is this?
10.
10.
Yeah, this is
10.
Yeah, good stuff. So this is 10. So effectively what we're saying is, for us to get the decimal number here, we are going to have to multiply 10 by 16. And then 7 by 1, because it's 16 to power 0, 16 to power 1. So effectively, we're adding 160 plus 7, which is 167. So here's the thing. What we're trying to do is, in here, this question is asking us to evaluate 107 plus 167 in binary. That's one way of looking at what we're doing here. And just to confirm that we're doing the right thing, we're just going to see 101, 00111. Convert this to decimal, we have 167, right? So effectively, what we're hunting for is 167 plus 107. The answer, what we want, whatever we get here should be equal to 274. Okay? This is what we want. But fear not, it turns out that it's a lot easier to do binary addition. Why do you think don't you see that it's a lot easier to do binary addition? There's nothing like, oh, the answer, because it's a hundreds place, the answer is 1 carry, is it 1 carry, is it 0 carry 1 or something, or 6 carry 1? Yeah, remember what you do when you have a decimal number like 1, sorry, 160. I'm trying to think of 169. 169 plus 9. You have large numbers like, oh, the answer is 8, carry 1 or something. But with a decimal, you only carry 0 and the 1. You're carrying 0 and the 1. This is what makes it fun and easy, actually. But anyway, so let's say we want to add this using binary addition. We follow the rules. 1 and 1, simple rule. 0. Again, please pay particular attention to the carry row and the result row here. When we add 1 and 1, the answer is 0, we carry 1. And look at this. We now have 1, 1, 1. 1, 1, 1, the answer is 1, we carry 1. 0, 1, 1, the answer is 0, we carry 1. 1, 0, 1, the answer is 0, we carry 1. 0, 0, 1, the answer is 1, we carry 0. Right? Why did I not carry the 0 there? I don't know why. Oh, it is. 0, 0, 1, the answer is 1. There's no, it carries 0. 1, 1, 0 is 0. We carry 1. 1, 0, 1 is 0. We carry 1. 0, 1, 1 is 0. We carry 1. And then we're just going to drop down the 1 because it's an overflow. So our answer is 1, 0, 0, 0, 1, 0, 0, 1, 0. Right? So what we're saying is effectively when we're adding these numbers, this is what we come up with. And really we can confirm this by just going to a calculator and just say, because it's 274, what is 274 in binary? 1, 0, 0, 0, 1, 0, 0, 1, 0. Yeah? Do you think, I mean, so the rules, right? I'm going to pause here and just find out if people are a bit confused with the rules here. I don't know. Do you think this is very confusing or something? Is this making sense?
It is trying to make sense, but the rules are a bit confusing. 1 plus 0, 0 carry 1. Kindly go over the last part. Just the addition. Just the addition.
1 plus 0 is not 0 carry 1. 1 plus 0 is you just drop down 1 carry 0. See, these are the dropping down is like the answer anyway. So here's the thing. These are the rules here, right? Simple rules here. I won't use this thing. I'll go to the actual rules that we have here. These rules here. Well, let me just delete this. Look at this. These are the rules we're working with here, Master Leandro, right? And whoever else is a bit confused. I know it can be confusing at the beginning, but like most things in life, practice makes perfect. These are the rules here. When you have 0, when you're adding 0 and 0, the answer is 0. You don't carry anything. When you're adding 1 and 0 or 0 and 1, the answer is 1. You carry 0. When you're adding 1 and 1, because 1 and 1, there's an overflow here. You can't have 2, right? 1 and 1 is, there's an overflow, you're saying it's 0. Carry 1. Do you understand this? When you're adding 1 and 1 and 1, the answer is 1. And then you carry 1.
I get it.
And by the way, these rules are best perceived.
I get it.
These rules are best perceived from the perspective of adding 3 digits, 3 binary numbers, not 2. Because in fact, when you're adding numbers, this is what you're going to be faced with in most instances, right? Where you begin by just adding 2 bits, but as you are carrying these things, you'll be working with 3. Which is why we had that thing that was showing you the different patterns associated with adding 3 binary digits. Good stuff. Okay. All right. So, but it turns out, right? I mean, I guess for people that are obsessed with the exam and but what about the exam and the test or something? In the test, it's not like you'll be told what is 1 1 plus 1 1. Yeah, nobody does that, right? Maybe they will tell you this, right? Whoever they are, they'll say evaluate 109 base 10 plus 136 base 10 using binary addition. Implicitly, what you're being asked to do is you convert 109 into binary, you convert 136 into binary or into base 2, and then you add them using binary addition, right? Perhaps a question would be flipped in such a way that the number is represented in base 16 here, and then you're saying add using binary addition. So you convert them into binary, and we know that this is easy, right? You're converting 109 into binary, just repeatedly divide by 2, and then you'll come up with the answer, and then that's it, right? Oh, and there's a solution here, actually. I didn't know. So you convert your 109 to base 2, right? Using repeated division. This is second nature now, where you're saying you repeatedly divide 109 by 2, and then you come up with this answer here, 1101101, right? And then you convert 136 as well, right? To base 2. And then you come up with this answer, 10001000. Now you notice that what I've done here, what's been done here is I'm using 8-bit representation because I know that 136 is a significantly large number. Because it's a significantly large number, when I'm adding these two numbers together, it's a lot easier when I represent them using the same bit representation. I don't know if I'm making sense. If you look at 109, it's represented using 1, 2, 3, 4, 5, 6, 7-bit representation. For my addition, if I'm using this step here, for my addition to make more sense, if I'm doing this for the first time, I want to make sure that I represent these bits using the same bit representation, right? And then I lay them down like so. This is my 109, this is my 136, and then I go through the same sequence of events where I'm saying I will now 1 and 0 drop down 1, or the answer is 1, 0, carry 0. 0 and 0, it's 0. 1 and 0, it's 1, I carry 0. 1 and 1, carry nothing. 1 and 1, it's 0, carry 1. 0, 0, 1 is 1, carry nothing. 1 and 0 is 1, carry nothing. 1 and 0 is 1, carry nothing. 0 and 1 is 1, carry nothing, right? And you're done, really, right? So I don't know if... Yes, hi.
What if the other one has more bits than the other?
This is the kind of situation we have. Good question, by the way. It's like so, and I know, right? It's a bit hard for you to wrap your head around what we're doing right now because you're using this strange number system, right? But think about this for a second. How do we add when we have 16 and 3,300 and okay, what do we do in base 10 when we are told to say add 17 and 3,341? The way you are taught by Miss Banda is you are taught to say when you're adding these numbers, right? Well, usually you start with a large number, right? Apparently it makes more logical sense that way, but you can start with a small number if you want to. You were taught to say, put them down like so. Why am I doing this? You put 3, 3, 4, 1, and then you write 17 like so. This is what you are taught, right? This is what you do. And then you start adding them. So you do the same thing for a binary. Now here's the thing. If you want, actually, what you could have done is instead of padding it or prefixing it with a 0, you could have just said, I will always add the larger magnitude, the largest number, which is the one with more bits on top, and then have the lower one below. So effectively, what I'm saying here is that instead of, and it's a great question, by the way, because maybe it will lessen the potential of people making mistakes when doing this. So observe, if I come here and I say, we're going to add this number here and this number. Because one has less bits, you have two options, right? Why is this doing this? You have two options. It's either you say, I will add this. We're adding this and this, by the way. When you're doing whatever method, if you're using the method that Lighton is showcasing to you, you're going to say we will have 1, 0, 0, 0, 1, 0, 0, 0. like Mr. Morim taught you in spreadsheet applications, you can just highlight and double click, and then this thing will be squished for you, right? So you can do this. You can start with the largest number and then put the lowest number here, and then you say it's 1, 1, 0, 1, 1, 0, 1. In which case you don't have to pad this with a 0. But the reason I padded this with a 0 in this example is because I put the smaller number on top. When you have the smaller number on top, right? When you have the smaller number on top, it's going to be a lot easier for you to pad this with a 0 so that you don't get confused with the carry bits and whatnot. But you don't have to pad it with a 0 if you want to. It doesn't matter really. It's one and the same thing. Yeah, and then you start applying these. Padding it with a 0 will really help you with the carry process, right? Because this would be your carry, and then this would be your answer or something, right? So you're saying, what do you carry when you add 1 and 0? You carry nothing. The answer is 1. 0 and 0, you carry nothing. The answer is 0. 1 and 1, you carry nothing. The answer is 1. 1 and 1, you carry 1. The answer is 0. 0 and 0, you carry nothing. The answer is 0. 1 and 0, you carry, and I'm doing this wrong. I'm just going to undo this. So 1, you want to carry to the next placeholder. 1 and 0, you carry nothing. The answer is 1. 0, 0, 0, you carry nothing. The answer is 0. 1, 0, 0, you carry nothing. The answer is 1. 1, 1, 0, you carry 1. The answer is 0. 0, 0, 1, you carry nothing. The answer is 1. 1, 0, 0, you carry nothing. The answer is 1. 1, 0, 0, you carry nothing. The answer is 1. 0, 1, 0, 1, right? You carry nothing. And then this is your answer here. So really, it's, I guess it's, we will have to go back in time, guys, and start doing, and I know it can be, it will feel frustrating at the beginning, but you want to go back in time and do exactly what you were taught to do in grade 1 when you're adding numbers on that plain piece of paper with a pencil. I don't know if they use pens now in grade 1, but we were taught it was a privilege to use a pen in my time. We started using pens in grade 5. Who does that? But anyway, so if you want to get that plain piece of paper and start doing this on a plain piece of paper, and then once it sinks in, once you understand what's going on here, then you can do away with the paper. And by the way, here's the thing, right? One of the other reasons why I'm padding the 0 and whatnot, and is because once we start doing subtraction, you want to get used to what we're doing here, right? More rules, but you want to make sure that you get used to what we're doing here. Now, I was going to suggest that we transition to subtraction immediately, but I'm going to suggest that I guess we take it easy. We still have a few makeup sessions. So I'm going to let you think about this, practice, and then we'll transition to subtraction tomorrow when we meet at 17 hours, I believe. Unless if there are any questions. I don't know if tomorrow we are meeting at, yeah, we're meeting at 17 hours. So we continue with binary subtraction with more rules. There are fewer rules now, right? And then we shall hopefully tomorrow, once we go through subtraction, I think we should have time. We'll go straight into multiplication, and if we still have time, we will do division. And it should be wonderful, really. If we can finish number systems by next week, that would be beautiful, because we can already, yeah, I think we should be able to. We can do, yeah, I guess data encoding here. Okay, so if there are no questions, I'm going to leave you with this. Just go through this, make sure it sinks in, make sure you understand the rules, and then we'll continue with binary subtraction tomorrow. Okay, I'll see you tomorrow then. Thank you.
Bo, my man, Bo.
What's up, Leand? What's up?
1100. Nakamba